Hello, this is Math Models, Notes for 5-3, Exploring Data, Day 2. So what we're going to do is we're going to take data, like what we see in this table, and we're going to interpret and discover a few things about it. So first off, this table shows life expectancy for people in the United States from the years 1900 to 1990. The thing we need to identify first is our independent variables and our dependent variable. Independent means that it doesn't care about the other variable. And years will flow no matter what life expectancy is. So the years are the independent variable, which means that life expectancy is our dependent variable. Usually the independent comes first and the dependent comes second, which will help. Now we're going to find our equation of the best fit line. And because I see R down here, I want to make sure that my diagnostics are on. So to do that, I do second, and all the way down here at 0, you see the word catalog. So you hit that button. You go to the letter D, see that green D, and then we'll scroll the rest of the way down to diagnostic on. We're going to hit enter, enter, and now our diagnostics are on. We can go ahead and move along. Now, this even tells you we're going to use a linear regression, so just as a reminder, to do that you go to Stat, Edit, and you have your lists. Now to save some time, I have already put this list in here. I've got my years in L1, and I've got my life expectancy in L2. I'm just going to scroll through real quick, make sure that I haven't made any errors. I haven't made any errors. So we're done with this. We're going to second, quit to get out. And now we'll go back to Stat, over to Calculate, and number 4 is our linear regression. We'll hit Enter, and it gives us our line. So we're going to, of course, need to round this off. So y equals 0.326x minus 570.5. Just doing a little bit of rounding. I took 3 decimal places here. I only took 1 decimal place here. Reasoning for that is just I want to make sure I've got enough significant digits. 3 or 4 would be good. 1 or 2 would be good. Less than this probably wouldn't give you any sort of accurate answer. Now our slope, we take our first number, 0.326. For our y-intercept, we'll take the second one, which is negative 570.5. And our r value is 0.98. Just 2 values are good there. And so this is all the information that we can get from our linear regression. Now, we look at this, we see that our slope is positive. It's about 1/3. Our y-intercept is negative. It's pretty far down. And our r is 0.98. Now, last lesson we said that an r value of 1 means that the line is straight, or r value of negative 1 means that the line is straight. Today I want to go ahead and let you know that the r value tells us a little bit more than that. The higher the r value, the closer it is to 1, the better that this equation is of predicting life expectancy. So if this is 0.98, which is really close to 1, this is a good predictor. Okay? So I can use this and get good predictions out of this. Well, let's talk about the y-intercept. Well, the y-intercept would be when years equal 0. So, at year 0, our life expectancy would be our y-intercept. So life expectancy is negative 570.5 years. Which, of course, this does not make any sense at all. You can't have a life expectancy of negative, and it's definitely not going to be that negative. So, while this is a good predictor for the information that we see, it's not a good predictor for numbers that are drastically outside of this year of birth. Well, let's go ahead and see what we can do. Well, this is a good predictor from 1900 to 1990. So what would the life expectancy be for someone born in 1942? Well, I could look at the table, but I want the nearest whole number, so I need to actually use my equation. Well, this is an x value. So y equals 0.326. We're going to replace x with this year. So 1942 minus 570.5. And I can just type that directly into the calculator. 0.326, 1942 minus 570.5. And we get 62.59, which is about 63. And if we look back at our table, 1940 was almost 63 to begin with. 1950 was up to 68. This number falls between those, and so yes, this is good. Now, this number may change based off of, did you go 4 decimal places here? Did you go 2 decimal places here? The more accurate that you make this match what the calculator tells you, the more accurate your prediction is going to be. Nearest whole number is fine. Let's go ahead and do this again for 2005. We set it the same way, but instead of 1942, we're going to use 2005. So we plug this directly back into the calculator. I'm going to second enter. That pulls up my last result. And just change this to 2005. And now this says 83.18, which is about 83, because the 1 does not round. Which, we look, in 1990 it was 75. This is 83, quite a bit bigger for 15 years. So yes, this is a number that makes sense according to our table. Well, now we're going to get into something a little bit more difficult. Here we want to know is, what year were they born in if they were told their life expectancy was to live 67 years? Well, this is not an x value, this is a y value. So, we're going to plug this into y. Let's go ahead and see what this gives us. This says that 67 equals 0.326 x minus 570.5. And now, we're going to solve. We start by adding 570.5 to both sides. 67 plus 570.5 is 637.5 equals 0.326x divide by 0.326. And we get that x equals 1995.5. So the nearest whole number would be 55. It would be 1956. Which if we look up here, this says that 1950 was 68, and this is 69.7. So 67 is actually below that, which means that, 56, we're actually not terribly accurate here. This data does not fit this one. But this is the answer that we got. This is the answer we'll choose. A better answer might have been gotten from using more decimal places here. That would have given us a closer result. Or it could just be that right here we have a bigger than average gap, and so this data doesn't fit perfectly. It's not a perfectly straight line. So, our answers are, of course, are not going to be perfect. They're not going to be exact. This is just predictions. And with a 0.98, we have a pretty good predictor, but it will not always be 100% accurate. Let's go ahead and look at our next set of data on the next page. Here, we're talking about how many hours students have watched TV and what they scored on a quiz. So we're looking at this. We have our independent variable of hours. The student gets to decide how many hours that they've watched TV. The score would be a reflection of how much TV they watched. So that's the dependent. Our equation line of best fit, we're going to need to go to Stat, Edit. And again, I've already typed these numbers in just to speed the process up a little bit. I'm going to double check my numbers real quick, make sure that they are indeed accurate. They are. So we get out of there, we go back to Stat, over to Calculate, and down to number 4, which is our linear regression. We run the linear regression and we get y equals negative 1.355x plus 87.2. Again, I use 3 decimal places for the first one, 1 decimal place for the second. You can use more if you like. This is just what I prefer to use. You really don't want to use any less, though. Otherwise, your predictions aren't going to be as accurate. So our slope would be the negative 1.355, which, this being negative, means that more hours watched means a lower score. Our y-intercept means 87.2. We'll talk about that here. We'll talk about the y-intercept. But more importantly, our r is negative 0.37. Now this number is nowhere near 1. So this means that this is a bad predictor. Okay, we're going to get some really bad results because this number is so low, means that a linear plot is not accurate for this. Okay, so anyone trying to use this data to prove something is going out of their way, and they're basically lying to you. Well, let's go ahead and take a look what the y-intercept means. The y-intercept means that I have watched no TV. Okay, which is someone who watches no TV would have what score? Well, they would have an 87.2. Has an 87.2 score. So if they don't watch any TV, then they should have made an 87. Well, let's go ahead and we look at this and we go, well, this person made better than 87. He watched 8 hours. This person made an 88. He watched 12. This one made a 96 by watching 18. Obviously, this doesn't make sense, and it doesn't fit the data either. I want to reflect back to, this is a poor predictor. But we're going to use this anyway because someone wants to use this data, they really want to, even though we're going to laugh at them later. We're going to go ahead and humor them. It says if they watch 20 hours of TV, okay? They watch 20 hours of TV, so this is our X. What would their quiz score be? So we're going to replace X in our formula with 20. So Y equals negative 1.355 times 20 plus 87.2. Negative 1.355 times 20 plus 87.2 means if they watched 20 hours, they should have made a 60. Again, this information doesn't actually match the table. It won't because of the bad predictor. But that's the answer that it's asking for. Now we're going to look at this one. Well, if they made a 70 on their quiz, we want to predict how much TV they watched. Well, this is our Y variable, which means we need to plug it into Y. So instead of X, it goes here. So 70 equals negative 1.355X plus 87.2. To solve this, we're going to subtract 87.2 from both sides. We get 70 minus 87.2 is negative 17.2. Is negative 1.355x. We divide by that number. And we get that x equals, 12.6. We're just going to call that 13. So according to this, if I made a 70 on my quiz, then you're telling me I watched 13 hours of TV. Now, this is how you do this. The calculator does a lot of the work, at least for the first half. The second half just requires plugging numbers in. So, shouldn't be too hard. Good luck on your assignment, and have a good day.